The next example discusses linear dependence and linear independence. Now this is a really important concept for vectors, and I've put down a lot of the notes here from the textbook because it summarises it really nicely. So the first part here it says is a set of vectors is linearly dependent if one of its members can be expressed as a linear combination of the other vectors. Now what that means is if you had, let's say just with two vectors, let's say we had the vector A and we had the vector B. If two things are dependent or linearly dependent, then what that means is that one of the vectors can be written as a scalar multiple of the other vector, where k is some number, some real number. Okay, what that could mean particularly then is perhaps, A is 3 times B. So maybe if A was written as a column, maybe it was 2 and 3. Maybe B, and that's A, maybe B is 3 times that, so you'd have a 6 and a 9, like that. So what dependence is really saying is that one of those vectors is actually dependent on the form of the other to give its expression. So if you were looking at 3 vectors, so here we've got A, B and C, you'd actually be able to write one of those 3 vectors in terms of the other 2 purely. So it really means you don't actually need both of these vectors. It's enough to really express this B in terms of A. You don't really need to know anything about B. You know it's just directly related to A. They're dependent on one another. If you have vectors that are linearly independent, that means that the vectors cannot be written as multiples of each other, so they're completely distinct. So for example, if you had some vectors that were linearly independent, I'll just put this here, so linearly independent, you might have something like -1 and 4, and that's independent from a vector like this, -2, I'm timesing by 2, but then on the bottom I might do something else, 1. Okay, there's no way that I can get from here to here, and that's just a question mark, from here to here by multiplying by some number, because I can't. So these two things, these two vectors or column vectors would be linearly independent. Okay, there's 2 simple facts here about linearly independent vectors. And the first one is that if you have the 0 vector in a set of vectors, that the vectors will be linearly dependent. And the reason for that is this: if you had A equals, and it's a vector, doesn't matter what it is, 1, 2, and you had B was the 0 vector, 0, 0, you know that you could actually write B in terms of A. How could you do it? You'd be multiplying, you'd be multiplying A by 0. That will give you the 0 vector. So that means that you could write A and B in terms of one another, 0A. And as soon as you can do that, as soon as you can write one vector in terms of the other as a scalar multiple, they're dependent. They depend on one another. It says here too, a set with exactly 2 vectors is linearly independent if and only if one vector is not a scalar multiple of the other. And we showed that before. So if you have a scalar multiple, like for example we had to start with A and B was 3 times B was equal to A, those 2 vectors were dependent because you could write one as a scalar multiple of the other. Now for 3 vectors it gets a bit more difficult. And this is where you really have to think about the practical way of determining this. So if you have 3 vectors, look for 2 vectors that you believe to be independent, i.e. not parallel. And actually I didn't say this before, but remember that if one vector is a scalar multiple of the other, so k is a real constant, this means that A is parallel to B. That's what this expression means. So when we talk about dependence, linear dependence actually means that the 2 vectors are parallel. Independent vectors are not parallel. Okay, so if we look at 2 vectors A and B in a set of 3 and determine that they are actually not parallel, then what we can do is we can use this expression here, and I'm going to put a red box around this. This is a really useful one, which is your third vector C. If you have vectors that are linearly dependent, you should be able to write your third vector C entirely in terms of A and B. We know A and B are independent, okay, because we look at them and we determine, yep, they're not scalar multiples, that's cool. And then we look to see whether this expression is satisfied. If this is satisfied, then our vectors are dependent. If this is not satisfied, they are independent. So dependent, remember, is that the vectors depend on one another in an expression. They can all fit into this expression.